This is the answer to homework 4, question 2. So question 2, there's x, which is a random variable that is uniform between -1 and 1. We're also given that y is equal to g of x, and that the density function is e to the negative y u of y. And then it asks us to find g of x. So essentially this looks like an inverse problem, and so some theorems that we pull out of the inverse problem in the textbook is that that the inverse function of the inverse of a distribution function is equal to y, which is kind of what we have since we have y is equal to g of x. We need to find g of x. And we're given a density function. And we're also given an x. And so the probability of g of x less than y is equal to the cumulative distribution function of y, and then fy of g of x is equal to f of x in the inverse problem. And so when we draw this out, essentially x ranging from -1 to 1, we know that the area of this entire area is 1, and so if we know that this length from -1 to 1 is 2, that must mean that the height is equal to 1 over 2. It's just the area divided by the width. And so then using that, we can see that when we draw out the distribution function from -1 to 1, we have the slope of 1 plus x over 2, and then we're equating that to 1 minus e to the negative y, which in that whole thing we're equating to fy of y, kind of like we pulled out and explained here in the theorem. And so from there, it's kind of just a plug-in check problem. So we have 1 plus x over 2 minus 1. So if we're basically trying to isolate for y, right, because we said that y was equal to g of x. So 1 plus x over 2 minus 1 is equal to negative e to the negative y. And then if we divide by -1, we have 1 minus 1 plus x over 2 is equal to e to the negative y. We take the ln of both sides, and we solve for y. You essentially end up with y is equal to negative ln of 1 minus x over 2, and that's g of x. So that's basically the problem solved right there. But if we kind of add on to this with a little bit of an explanation, well, here we have the drawing, and then here, so that this is in terms of x, and we draw it in terms of y. Instead, we're drawing so it still tapers off at 1, but we have 1 minus e to the negative y. And so this g of x actually is also only valid between -1 and 1, because we said x was uniform in that interval. So everywhere else, we kind of have to, you can infer it by drawing it. I really like to work with the numbers. So if I solve for x at -1, if I plug in -1, you end up with ln of 2 over 2, which is just ln of 1. And so that's at any, if basically when x is less than -1, g of x is going to be equal to 0, including at -1. And then when x is equal to 1, you end up with ln of 0, which is undefined. So when you draw it out, if you draw out y equals -ln of 1 minus x over 2, you see that g of x is actually approaching infinity once while x is approaching 1. So because the function is undefined at 1, you kind of end up with this vertical asymptote that has the function approaching infinity.